Hello, and thank you for joining today's presentation in the Richardson RFPD webinar series, A Walk Around the Block. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presentation. Richardson RFPD is an aeroelectronics company. It is a specialty electronic component distributor focused on the RF and wireless communications, industrial IoT, power conversion and renewable energy markets. With its global reach and extensive technical capability, Richardson RFPD serves its customers through component development and selection, technical support, and world-class logistics and supply chain capabilities. Richardson RFPD had a few simple objectives for its Walk Around the Block webinar series: to organize concise webinars of no more than 20 minutes around an engaging topic, make it applicable to the global engineering community seeking solutions for design challenges, and to feed this community's hunger for information on innovative technologies to help differentiate their own products. In today's session, Jack Lamar, Automotive Marketing Manager for Discrete Power Products at Wolfspeed, will offer an overview of the benefits of Wolfspeed silicon carbide and modern onboard chargers to maximize efficiency and power density while minimizing system cost. So without further delay, let me turn it over to Jack Lamar. Jack, go right ahead.
Hello everyone, my name is Jack Lamar and I'm the Automotive Systems Marketing Manager for Wolfspeed's discrete power device business. And today I'll be walking through this webinar of Wolfspeed silicon carbide in OBCs, or onboard charger systems, for electric vehicles. So let's go ahead and jump in. Here are the topics that we'll cover in this webinar. We'll start with answering the question of why silicon carbide as a technology, and then we'll move on to, then why Wolfspeed? And moving through some OBC system design trends, we'll then talk about what are the specific advantages of using silicon carbide and how this technology can enable the design improvements in onboard charger designs. So let's begin with a brief overview of the basics of silicon carbide. SiC is a semiconductor-based material, and specifically a wide bandgap material. This means it has intrinsic physical characteristics that make it ideal for high power, high temperature, and high frequency operation. Today we will focus on SiC power devices such as MOSFETs and Schottky diodes. However, SiC can also be used as a base material for radio frequency or RF devices. Now, as I said previously, the intrinsic properties of SiC enable it to perform better than traditional silicon in many areas. For example, SiC has significantly lower overall on-state resistances, allowing more current to flow and less power to be lost through heat in the process. SiC can also operate safely at much higher voltages, and as we all know, higher voltage and higher current means more power converted. Silicon carbide can also safely operate at high frequencies, with minimal losses due to the fact that it has no minority carriers. This allows a SiC device to more closely resemble an ideal switch and do so at much higher frequencies than silicon devices. And lastly, SiC can operate at much higher temperatures due to its lower thermal impedance. This is especially important in rugged or extreme environments that are often required for automotive or commercial industrial equipment. So the implications of all these characteristics are that for end systems such as onboard chargers, SiC enables lower losses, smaller size, and lower overall cost, even compared to silicon-based systems of the past. Okay, so now that we know the advantages of silicon carbide as a technology, let's answer the question of why Wolfspeed. We know that there are many suppliers out there now who have silicon carbide portfolio offerings for power devices, but we really believe that we stand out. So what you'll see here is that Wolfspeed is the clear industry leader and expert when it comes to silicon carbide power. We invented the SiC MOSFET in 2011 and a proven track record of success with over 30 years and 7 trillion hours of power devices in the field. We are making huge investments to continue to lead SiC adoption and production in automotive, industrial, and energy markets, and you may have seen a lot of those announcements in the news. We are 100% dedicated to helping our customers maximize the performance of their systems with SiC, and we have the proven expertise to do so. So we not only focus on the silicon carbide devices themselves, but we have a great team of system design experts that can help our customers optimize and make their designs the most efficient possible. So all in all, Wolfspeed is a proven leader in silicon carbide and has the resources required to really enable customer success. Okay, so let's move on specifically to how silicon carbide makes a difference in onboard charger design. So we'll start with a brief overview of what an onboard charger system is. What an onboard charger does is supply power from an AC source. It converts that power from AC to DC to be sent to the electric vehicle battery. This can be unidirectional, meaning the power just flows into the battery to be used by the vehicle, or it could be bidirectional, meaning it could flow into the battery, but also in the reverse direction to supply power to auxiliary functions or other vehicles or the electric grid. Now, it can also range, an OBC can range from 1 kilowatt power delivery for e-bikes and scooters all the way up to upwards of 22 kilowatts for things like buses and commercial vehicles. And so the advantages of silicon carbide in these systems are pretty clear. With the lower losses, with the smaller size and the greater power delivery, you can minimize the size, weight, and the cost of the OBC design, all while maximizing the amount of power delivered to the battery. So let's dive into the block diagram of these systems. We'll start with a silicon carbide based unidirectional onboard charger. In this system, the power flow goes from the source through the OBC and into the battery. In the bottom left, you can see a common approach with SiC MOSFETs and diodes used in both the totem pole PFC and the DC to DC converter. Unidirectional designs are lower cost since you can use diodes instead of MOSFETs, and will likely be the majority of OBC systems in production over the next 5 to 10 years. Wolfspeed MOSFETs and Schottky diodes can deliver the maximum efficiency and power density while maintaining the system cost of unidirectional OBCs and really minimizing that system cost. So now let's move on to bidirectional onboard charging. So again, this is similar to a unidirectional OBC, but we've replaced all of the diodes with MOSFETs to enable bidirectional power flow. Bidirectionality charging is being pushed by some EV initiatives worldwide, primarily in Asia, because it enables kind of a V2X architecture of the power grid, where vehicles can be used to balance out the power grid and also supply extra energy to other electric vehicles that may be stranded on the road if they lost all their charge. So here we show a brief overview of all the different system design trends that we see out there. Now, as I said before, an OBC power level can range from lower power from 1 to 3.3 kilowatts all the way up to 22 kilowatts. And this is depending on things like the vehicle type, the battery size, and even how fast the car manufacturer wants their vehicle to charge. So as we can see here, there are other technologies, other semiconductor technologies out there in each of these spaces. And really, when it comes to silicon carbide, as you increase in power, the value for silicon carbide continues to increase and increase. For customers, each of these system designs are going to enable or require different key care abouts. So for a lower power system such as a e-scooter, really going to care about power density because it needs to be as small of a form factor as possible, as well as cost. And so you can see kind of the order of the key care abouts throughout all the different types of systems. So one thing you notice in all those key care abouts is that cost is always a main concern. So what we hear in the industry is that many customers and partners a lot of times have this impression that a silicon carbide solution is way more expensive than a traditional silicon solution. So let's dive into that and let's answer the question, is SiC really a more expensive design? So okay, let's look at the cost breakdown of these two systems. This is a silicon-based 6.6 kilowatt bidirectional OBC design using traditional IGBTs. Notice the input PFC is switching at 20 kilohertz with the IGBTs, and the DC-DC is at a resonant frequency of about 100 kilohertz. When I go to the next slide, we'll see the difference there. So on this slide, we can see that with silicon carbide, the designer is able to increase the switching frequencies of both the PFC and the DC-DC leg. And what this does is it allows you to use smaller magnetics and overall a smaller system design, which impacts both the power density and the cost, as we'll see on the next slide. So here's the overall cost breakdown of the two systems. And what we see here on the left is that actually the silicon-based OBC can be up to 15% more expensive than the silicon carbide-based system. And this is just with power stage components. On top of the lower BOM cost, the SiC system also has an efficiency advantage, comparing the 96 average system efficiency to 94%. And this advantage really can be quantified into a cost savings that is passed on to the consumer. So with this comes basically you're wasting less energy and therefore less money in the power conversion process. And that'll play itself out over the lifetime of the vehicle. And then the last benefit, but also just as important, is the power density. So these, for a same power system, you can fit much more into a given space, and that is essential for EV manufacturers who are really trying to maximize the space and the weight of their vehicle. So okay, we're starting to see that SiC as a technology can enable some meaningful improvements in OBC system design. But now let's talk about the question, how should I choose one of the many SiC providers? As we said before, Wolfspeed was the first to the silicon carbide power game decades ago, but many other players have jumped in since. What we've done here is given a brief outline of the competitive benchmarking tests that we've done against many of our main competitors, their devices, and their technologies. So the key here is what we want to do is help our customers understand the whole system experience for specifically for a wide bandgap technology device in their power system. So what we've done is in these competitive analysis decks, we've compared datasheet parameters, so just head-to-head on a datasheet what you see, but then we've taken it a step further and done lab bench measured data comparisons as well as in-system performance. What this helps customers understand is that datasheets don't always tell the whole story. Different parameters are tested at different conditions and datasheets, so it's not always an apples to apples comparison. And so what is really important is seeing what these devices look like, both from a efficiency, reliability, and thermal perspective in an actual system. So that's what we've done here. So the competitive benchmarking is one example of Wolfspeed's system expertise in onboard charger design. And this is another one. Wolfspeed has developed a few reference designs that customers can use to test and evaluate our devices in an end system. The main one we use for onboard charger design is our 6.6 kilowatt bidirectional OBC. And this was the design that was used in the cost analysis that we talked about a few slides ago. This uses 14 of our C3M 60 milliohm 650 volt silicon carbide MOSFETs in the 3-lead TO2473 package. It has a 3.3 kilowatt per liter power density and a high efficiency. And we have hardware units and a full paper design available for customers to use. Now, we also are in development with a higher power 22 kilowatt 3-phase bidirectional design. And this will be developed in 2 blocks. It'll be first, we will have the DC-DC block available. And then later this year, we will be coming out with the AFE block. Now, those are obviously for bidirectional OBC designs if customers are interested in that. If they're going down the unidirectional route, they can still use the bidirectional system and do simulations and evaluate what a diode architecture would be like, replacing some of those MOSFETs with diodes. Or they could take some of these blocks and test out the blocks independently. So we have a 2.2 kilowatt bridgeless totem pole PFC using the same 650 volt MOSFET and actually silicon diodes, and can be used to kind of evaluate what this would look like in an onboard charger. This would be a lower power onboard charger system. And then we have a DC-DC block for the higher power unidirectional for 6.6 kilowatts. So all this to say that Wolfspeed has significant expertise in both device design from our decades of experience, but also in system design with a applications team who has applications engineers from many different industry leaders, power design manufacturers out there. So we are happy to help our customers get a leg up, get faster time to market, and build better, more efficient design. In terms of product offering, much of what we covered today and what applies to OBCs are discrete MOSFETs and diodes. But what we show here is we also offer a wide range of power module and bare power die products to meet various market requirements and demands. So our discrete products that we focused on today range from 650 volts all the way up to 1700 volts. We do have a lowest RDS(on) in the industry for our 1200 volt and 650 volt. For 1200 volt, that is a 16 milliohm device. Actually, for the 650 volt, it's 15 milliohms. And we have industrial and automotive qualified MOSFETs along with that, and diodes. When we move over to modules, so these are for higher power, sometimes more optimized designs. So we have standard footprint modules, as well as the one that's shown here is Wolfspeed's XM3 module that is optimized for silicon carbide. And then lastly, for strategic module manufacturers and vertical integration, we have bare die products that can be sold to customers. Okay, so I hope this short webinar was very informative for you and that you have a better understanding of how silicon carbide MOSFET and diode technology really enables vast improvement in OBC system design in all these different aspects in efficiency, power density, and even cost. Wolfspeed also has extensive expertise in OBC design, and so this can help our customers bring their solutions to market as quickly as possible. And Wolfspeed SiC MOSFETs and diodes have industry-leading system performance, and so these are key enablers to maximizing OBC performance in the electric vehicle and improving the user experience for the consumer. So if you have any more questions, please visit www.wolfspeed.com or reach out to your local sales representative for more information. Thank you so much for your time and have an amazing rest of your day.
Thank you for attending today's webinar in the Richardson RFPD A Walk Around the Block series. Thank you again to Jack Lamar for today's presentation, and thank you from both Wolfspeed and Richardson RFPD for attending today's session. Take care, and we will speak with you soon.